Hey guys, Mr. McKinney here, just doing our Unit 8 review video. This is my second attempt. As you will see, a lot of the slides are already filled in because I recorded 15 minutes and then realized that the mic wasn't working. Hopefully it's working this time. Here we go. We're doing derivatives. This was Unit 8, but really this was all of first semester. All right, here we go. The two new rules we added to start out this unit were the derivative of cosecant and the derivative of secant. You need to have all 6 of these rules memorized, though. They're all on our cheat sheet, and you should have them all memorized. We're going to go through a few examples. So find y double prime means find the second derivative. So the first derivative of secant is secant tangent. The second derivative means we need to use the product rule here. So secant times the derivative of tangent, and then tangent times the derivative of secant. For your response, you could stop here. Otherwise, you need to simplify it to one of these other versions. For the derivative of tangent of 7x, we need to use the chain rule here. So derivative of tangent is secant squared. Make sure you don't change the inside function yet. And then the derivative of 7x is 7. It's fine either of these ways. You can either move the 7 in front or leave it out at the end. Just make sure you have parentheses. Okay. The equation of a line tangent to a function. So anytime you're asked to find the equation of a line, make sure you're using point slope form. So point slope form is down here. Y minus y1 equals m times x minus x1. You need a point and a slope. The point is going to come from the original function. The slope is going to come from the derivative. The derivative of f is f prime. So the derivative of cosecant is negative cosecant cotangent. So if I want to know the slope at this point, when x is pi over 4, I'd plug in pi over 4. Now technically negative cosecant of pi over 4, cotangent of pi over 4. This is okay on the free response portion of the AP exam. You could stop there. And you could put it into your answer there as well. That's my slope. This would likely be on the multiple choice portion, so we need to be able to simplify it without a calculator. Think about a 45-degree angle. So cosecant, which is 1 over sine, would be 1 over root 2 over 2, which is 2 over root 2. We had a negative out front. Cotangent would be 1. The point on the original function, cosecant of pi over 4, again, cosecant's 1 over sine, so 1 over root 2 over 2 would be 2 over root 2. Again, you could leave your answer as cosecant of pi over 4 on the free response portion, or you can plug everything in. Velocity, again, is the derivative of distance. Notice that if we have cosine of t, we're not using the product rule, we're using the chain rule. Because this is a composition, f of g of x. And the derivative of that is f prime of g of x times g prime of x. So you don't change the inside until you're multiplying by the derivative at the end. So this cosine stays the same, and then I multiply by the derivative of cosine. To find the velocity at a specific time, after you take the derivative, just plug that value in. Again, you could stop here on the free response portion of the AP exam, but this would likely be part of a multiple choice question, and you'd need to be able to figure out that it's 0. To help myself when I'm trying to evaluate sine and cosine, I sketch a little sine or cosine graph and think about what's happening. Other than the new rules on cosecant and secant, we also learned the derivative of a to the power of x. We already knew e to the power of x, and really it's the same rule, which is you have to multiply by natural log of the base if a is any constant other than e. And really it's the same thing as if we're doing it by e, because natural log of e is just 1. This is just the chain rule down here. So these were the new rules we learned regarding exponentials. Here's an example. So 9 times 4 to the power of x squared. The constant that's being multiplied can just move down. And then when I take the derivative of 4 to the power of x squared, first of all, an exponential always moves down. and then we need natural log of the base, and then we need the derivative of the exponent. So that's the chain rule here. Either of these is acceptable. This was probably the way you would see it on a multiple choice exam. The last rule that we learned at the start of this unit was log of a base other than e. We already knew the rules for natural log, which is really a base of e. And then if the base is not e, you multiply by 1 over ln of that base, or basically you divide by ln of that base. So when we were doing an exponential, you multiplied by ln of the base. When you're doing a logarithmic, you divide by ln of the base. And again, you can think about that rule. It does apply on the natural log, because if you do 1 divided by ln of e, that whole thing goes away. It's just 1. And again, if you have a function on the inside, then you put that function on top, or I would think about it as like 1 over u ln of a times u prime. I think about it as the chain rule. This is just the chain rule rearranged. Here's an example of how to do logs with different bases. So log, if there's no number written, means log base 10. So I'd need a factor of 1 over ln of 10. Log base 4, I'd need a factor of 1 over ln of 4. And then simplified. There's another way to think about this problem, which would be to expand it. So this is just an alternative method down here. So you could expand it first. You end up with some constants that go away when you take the derivative. You're going to get the same answer either way. So this is for those of you guys that like to check your work. All right, so the next section we got into was the technique of logs. So the first problem we looked at was y equals natural log, and we have a square root on top and then an exponential on the bottom. Now, in theory, you could have done natural log, so 1 over the inside function, and then times the derivative of this, and we'd use the quotient rule, but that would get really ugly. So instead, what you're going to want to do is split it up into 2 separate functions, and then this is just using log properties. Notice I haven't taken the derivative yet. So the first log property says that you can use division in 1 log and split it into 2 logs that are subtracted. And there's another log property that says you can move the exponents in front if you have a log. At this point, you can take the derivative, and it's a much simpler function to be dealing with. This is the same problem we did in a different video, so I'm not going to simplify it again. Now, that problem could have been done without logs, but there are certain problems that you have to use the technique of logs. And the technique of logs is where you add a natural log on both sides to make the problem easier. So this one doesn't have a natural log. And if we didn't know the technique of logs, we would start doing the quotient rule, and it would get really ugly really quickly. So we're not going to use the quotient rule. We're going to take the natural log on both sides. When we take the derivative of ln of y, it's going to be 1 over y times y prime. On this side, we just did that problem, the derivative of natural log of this fraction. So you'd split it up first and then take the derivative. Now to get rid of this 1 over y part, you're going to multiply each side by y. So over here it'll cancel out. And then instead of y, I'm going to plug that original function back in. And then this is the derivative of this part, simplified. So the technique of logs makes this problem much simpler. Again, you could use the quotient rule with the power rule and the chain rule, but it would get really ugly. A problem like this, tangent of x to the power of x, you have to use the technique of logs. So if you see an exponential where the base and the exponent, so the base and the exponent are both variables, that's when you know you have to use the technique of logs. So if you have x to the power of x, or sine of x to the power of x, or x to the power of cosecant of x, so if the base and the exponent both have a variable in it, that's when you're going to have to use technique of logs. So technique of logs says take the natural log of both sides, and then because you've taken the natural log, you can move this variable in front and turn it into a product rule problem. We don't know how to take the derivative of this problem, but we know how to use the product rule. So we use the product rule, x times derivative of natural log is 1 over times derivative of the inside, and then derivative of x is 1 times natural log of tangent of x. Again, on the left side, derivative of natural log of y would be 1 over y times y prime, so we'd multiply both sides by y. So my final answer would have the original problem in it, tangent of x to the power of x. If I simplified this, I'd get x secant squared over tangent plus ln of tangent of x. So again, use the technique of logs when the base and the exponent both have variables, or when you have a really ugly fraction. All right, so that's where I would have gotten in 15 minutes. So it's a little bit faster if I have everything filled out, but possibly not as helpful. Anyway, picking up from here, we got into Lapitals Rule. Lapitals Rule helps you evaluate limits if it's an indeterminate form. And the ones we need to worry about in this class are 0 over 0 and infinity over infinity. And those can be positives or negatives. There's other versions involving like 0 to the power of 0 or 0 to the power of infinity, but we don't need to worry about those in AB. They're not in AB. So if you're trying to evaluate a limit and you realize that the limit evaluates to be 0 on the top and the bottom of the fraction, or they can both be infinity, then you can use what's called Lapitals Rule, which says as long as both of these limit statements are true, they're both equal to 0 or they're both equal to infinity, then the limit of the original problem is equal to the limit of the derivative on the top and the derivative on the bottom. Note that this is not the quotient rule. This has nothing to do with the quotient rule. The quotient rule is if you're trying to take the derivative of a function that has a function on the top and the bottom. So if I was trying to find the derivative of y prime, that's where I'd have to use the quotient rule, and I'd have g squared, g times f prime minus f times g prime. The quotient rule has nothing to do with Lapitals Rule. Lapitals Rule is for limits. So if you see limit of a fraction, that's when you might be using Lapitals Rule. Make sure you write out separate limit statements for the top and the bottom. Okay, so for example here, if I was to plug in 0, I'd get sine of 0, which is 0, divided by 0. I don't want to write equals 0 over 0. I want to write out a separate limit statement for the top and show that that evaluates to be 0, and a limit statement for the bottom and show that evaluates to be 0. Because both of those evaluate to be 0, I can say LHOP applies. Make sure that you write out these three things though. A limit statement for the top, the bottom, and somewhere you've referenced LHOP. So then this is the same as the limit of the derivative on the top and the bottom. So the derivative of 7x is 7. Derivative of sine of 7x would be cosine of 7x times the derivative of 7x, which is 7. Cosine of 7x, if I plug in 0, so now I can actually plug in 0 because this 7 is not going to be 0 no matter what. So the 7's cancel. Cosine of 7 times 0 is 1. Now I could just say that my answer is cosine of 7 times 0 also. That's acceptable on the free response portion of the AP exam. Again, make sure you don't write equals 0 over 0. And then write out limit statements and reference LHOP. Sometimes you'll have to use LHOP more than once. All right, so I went ahead and worked it out. I kind of ran out of space because I forgot you had to use LHOP a bunch of times on this problem. So the original limits both equal 0, so we use LHOP, take the derivative on the top and the bottom. Both those limits still evaluate to be 0, so we use LHOP again. Both those limits evaluate to be 0, so we use LHOP again, and then that evaluates to be 24. Each time you use LHOP, make sure you write out the limit statements twice, and then make sure you reference LHOP, and make sure you never write equals 0 over 0 or infinity over infinity. I'm going to work through these two. So as we can see on both of these examples, the top and bottom limits both evaluate to be infinity. So again, don't write equals infinity over infinity. Write out the limit statements and reference LHOP. In this case, this would turn into just x, so the limit as x approaches infinity of x, which is infinity. This one turns into